So hi all, welcome to the open source models with Hugging Face course from Simplilearn. So in this journey, you'll explore powerful open source models across diverse domains. You'll learn to select the right models for NLP tasks like translation, summarization, and embeddings, as well as audio applications such as ASR and Text-to-Speech. For computer vision, you'll dive into object detection, segmentation, retrieval, captioning, and multimodal VQA, along with zero-shot techniques. And by the end, you'll have the skills to implement these models effectively in real-world projects. So let's get started. So basically, the open source machine learning models are now more accessible than ever, with new ones being released every week on the Hugging Face Hub. So basically, Hugging Face is the AI community. So this platform serves as a central repository where you can find pre-trained models, data sets, and machine learning demos, commonly referred to as Hugging Face spaces. But there are thousands of models available. So how do you find the one that best fits your project? So let's have a walkthrough of it. To begin with, you can head over to the Hugging Face Hub and navigate to the models over here. So this is your models page. So you'll find models designed for a variety of machine learning tasks. The sheer number of options may seem overwhelming, but don't worry. There's a structured way to narrow down your search. As you can see under multimodal, we have audio text-to-text, image text-to-text, we have VQA, then we have visual document retrieval. Now under computer vision, we have depth estimation, we have image segmentation, we have video classification. Now under natural language processing, NLP, we have text classification, we have question answering, we have translation, and then in audio we have, automatic speech recognition, voice activity detection, we have reinforcement learning. So for now, we'll just use an example of automatic speech recognition. So you can select, so this in the left side, okay? So in the left side panel, you can select the model. I'll go with this model for now. Suppose if you want the model that transcribes speech in French, you can further filter your search. As you can see here, you have languages. So for example, we can take French and you can filter out the models according to your needs. Now, another key factor to consider is a model's license type. So if you need a model for commercial, here you can find licenses. So for example, if you want a model for commercial use, you'll want one with a permissive license, meaning it can be used freely in most applications. But however, this will significantly limit your choices compared to models with more restrictive licenses. Now to further refine your search, you also can sort model based on downloads. As you can see here in the right corner, you have trending, most likes, most downloads, recently created, recently updated. So for example, here we have kept trending, which means recently developed models that are gaining attention. You can also go to most downloads, where you'll be able to find popular models widely used by the community. So let's just select a model and see further details. So as you can see, when you select a model, you'll find a model card. So before you decide which model to select, it's always better to have a look at the model card. So basically, model card acts as a README file, providing crucial details like model's architecture, how it was trained, limitations, etc. So as you can see, it has the model summary, has the intended users, it has listed its primary use cases, use case considerations, it has given its model quality, and there are so many parameters it has described. And also models on Hugging Face come in different sizes, referred to as checkpoints. So a checkpoint includes the model's pre-trained weights and configuration details. So for example, some have millions of parameters and others have billions, making them more resource intensive. So you can also check that out before deciding which model to select for your project. Now another way of exploring or alternate ways to explore models is by directly going to the task page over here. Here in this menu bar, you can find the tasks, where again, this page categorizes machine learning tasks, making it easier to discover models for specific use cases. So for instance, if you're interested in automatic speech recognition, again, we can go down, you can select it. And as you can see, it actually gives a detailed explanation of the fundamentals of automatic speech recognition. It suggests models optimized for tasks. It lists relevant data sets. For example, here they have provided the data sets. It also provides interactive demos for testing models. So once you have chosen a model, you can load it using the transformers library. So let's just take a model and then explain. So as you can see over here, you'll find an option, use this model. So over there, you can go to transformers. So as you can see, the using transformers button on the model page provides code snippets that show you how to download and integrate the model into your workflow. So in this course, we'll primarily use the pipeline object to interact with models. The pipeline simplifies the process by handling all necessary pre-processing for different input types, including audio models, converting input into a log-mil spectrogram, text models for tokenizing text before processing, and image models for resizing and normalizing images. So using the pipeline eliminates the need to manually handle these pre-processing steps. So now that you got a basic idea of how to find and load models, let's get into the hands-on demo. So in this chapter, we'll be dealing with NLP or natural language processing. So natural language processing or NLP is a branch of artificial intelligence that helps computers understand, interpret, and generate human language. So you can think about how we communicate every day, like through text messages, voice commands, emails, or even social media posts. So NLP enables machines to process and respond to language in a way that feels natural, just like humans do. A great example of NLP would be chatbots. So you must have interacted with a virtual assistant like Siri, Alexa, or ChatGPT, right? So when you ask, what's the weather like today? Basically, the system processes your words, understands the context, fetches relevant data, and responds in a way that makes sense. And that's NLP working behind the scenes. Now, another common example is machine translation, like Google Translate. So if you type a sentence in English, and you want to translate it into French, let's say. So NLP helps break down the sentence structure, understand its meaning, and recreate it in another language while keeping grammar and context intact. So NLP is also used in spam filters, speech recognition like voice-to-text features on smartphones, autocorrect, and predictive text in messaging apps, and even in sentiment analysis. So where companies analyze customer reviews to determine whether people are happy or frustrated with their services. So in short, NLP is what allows machines to read, write, and understand human language, making interactions between humans and technology more seamless and intelligent. So now let's move on to how does NLP or natural language processing work. So as you already saw, NLP is what enables computers to understand, interpret, and generate human language in a way that feels natural. Human language is incredibly complex. Words can have multiple meanings, sentences can be structured in different ways, and context plays a huge role in understanding. So when we speak or write, we don't just string together random words. We follow patterns, use slang, and even convey emotions through our tone. So how does a computer which only understands numbers make sense of all this? Let's see. So the first step in NLP is pre-processing the text, which involves breaking down raw language into a structured format that a machine can understand. So imagine you are cleaning up a messy document before analyzing it. So this process starts with tokenization, where a sentence is split into smaller chunks or tokens, usually words. Then comes stemming and lemmatization. So here is where words are reduced to their root form. Like for example, running becomes run and better becomes good. So this helps standardize the text and ensures that different variations of a word are treated as the same concept. Now, another important step is removing stop words like is, the, and, which don't add much meaning to sentence but can clutter the analysis. Additionally, part of speech POS tagging labels each word based on its function, such as noun, verb, or adjective. So this is crucial because words can take on different meanings depending on their role in a sentence. So now once the text is cleaned and structured, the next step is processing, where the system tries to understand meaning and context. So one of the first tasks is syntax analysis, which looks at sentence structure and grammar. So this determines relationships between words, such as identifying the subject, verb, and object in a sentence. For instance, in the sentence, the cat sat on the mat. NLP recognizes that cat is the subject, sat is the verb, and mat is the object. But understanding sentence structure alone isn't enough. Computers also need to grasp semantics, which means the meaning behind the words. So this is where semantic analysis comes in, helping computers differentiate between words with multiple meanings. So for example, in the sentence, I saw a bat, does bat refer to the flying mammal or a baseball bat? So humans use context to figure this out, and NLP models are trained to do the same using large data sets and statistical analysis. Now, a major challenge in NLP is understanding sentiment and intent, especially in conversations or social media posts where emotions are involved. And this is where sentiment analysis plays a role, detecting whether a sentence expresses a positive, negative, or neutral feeling. So for example, for customer tweets, I love this product. An NLP model can classify this as a positive sentiment. On the other hand, a tweet like, was a terrible experience, I am so disappointed, would be categorized as negative. So sentiment analysis helps businesses track customer satisfaction, analyze feedback, and even predict trends based on public opinion. Now, another important aspect is context understanding, which ensures that a conversation flows naturally. So, for instance, if you ask a chatbot, what's the weather like today? Then follow up with, and tomorrow? So, NLP understands that tomorrow refers to the weather forecast rather than starting a new topic. So, advanced NLP models use deep learning to improve context retention, making interactions with virtual assistants like Siri, Alexa, and Google Assistant feel more natural. Behind the scenes, NLP relies on machine learning and deep learning models to continuously improve its language understanding capabilities. Earlier, NLP systems used rule-based methods, where predefined grammar rules dictated how a computer interpreted language. However, these systems struggled with variations in speech, slang, and new phrases. So now, modern NLP, on the other hand, is powered by neural networks and deep learning, which allow AI to learn from vast amounts of text data and improve over time. So models like BERT, which stands for bidirectional encoder representations from transformers, and GPT, which stands for generative pre-trained transformer, have revolutionized NLP by enabling machines to understand words in context rather than just individually. So these models are trained on massive datasets, including books, articles, and conversations, helping them generate responses that sound much more human-like. So to see NLP in action, consider how voice assistants work. So when you say, "Hey Siri, remind me to buy groceries at 6 p.m., several NLP steps happen almost instantly. So first, speech recognition converts your spoken words into text. Then intent detection determines that you want to set a reminder. NLP then extracts key details like the task, buy groceries, and the time, like 6 p.m., before finally executing the action. Now, another example is Google Translate, which goes beyond simple word-for-word translation. It analyzes sentence structure, grammar, and cultural nuances to ensure a natural-sounding translation. So as NLP continues to evolve, its applications are becoming more powerful and widespread. From chatbots answering customer queries to sentiment analysis tracking brand reputation, NLP is transforming the way humans and machines interact. The future of NLP is likely to bring even more accurate real-time translations, smarter virtual assistants, and AI-powered writing tools that feel indistinguishable from human speech. While challenges remain, ongoing advancements in deep learning are pushing NLP toward a future where machines truly understand language just like humans do. So now that you have brushed up the basics, let's move on to building a chatbot using Hugging Face transformers. So here the chatbot leverages a pre-trained conversational model called BlenderBot 400M Distill to engage in a back and forth conversation. So first we'll write the code and we'll break down each section of the code to understand its functionality. So first we'll be starting by installing the required library. So since Hugging Face Transformers library isn't a public built-in Python module, we need to install it. So this is the library. pip install transformers. It's showing like this because we have already installed it before in this environment. But while you are working, you have to install it. So next we have to suppress the warnings for a cleaner output. So by default, the transformers library may generate warnings or informational messages when loading the models. So these line of codes will suppress these messages to keep the output clean. So for that you have to write from transformers utils import login and set robustity So next let's import the pipeline function from transformers import pipeline. So the pipeline function from the transformers library provides an easy way to load pre-trained models for various NLP tasks like text classification, translation, summarization, and conversational generation. Now that we have imported the pipeline, next is defining the chatbot pipeline. So let's do that first. Chatbot is equal to pipeline task is equal to conversational. So here we initialize the chatbot pipeline using the BlenderBot 400M distill model. So let's just break it down for clarity. So this particular code task is equal to conversational. It specifies that we are building a chatbot rather than another NLP task like text generation or summarization. So as it is a chatbot, the tone or the style must be conversational, and that's why we have mentioned that. Now the next one, which is model, is equal to, and we have specified a model. So this loads the pre-trained model from the specified directory. So here we have used the BlenderBot 400M distill model. This is a lightweight version of Facebook's BlenderBot optimized for efficiency while maintaining conversational ability. So let me just speak a bit about BlenderBot 400M distill. So this is basically a conversational AI model that was developed by Facebook AI that can handle open domain dialogue. So this version is a compressed, distilled version of the larger BlenderBot model which exists, making it faster and more efficient. So basically it has been fine-tuned on large-scale conversational data sets. It does not retain memory of previous conversations. So each input is treated independently unless explicitly included. It also generates responses using an encoder-decoder architecture, meaning it takes an input, processes it, and generates a meaningful response. So now let's move into coding. Let's define the user's first message. So let's give a user's message. User message is equal to, let's ask which are some best places to visit during summer. So this variable stores the user's input message as a multi-line string. Now next, let's create a conversational object. So let's write the code first. From transformers okay, there's some error. Let me just fix it. Conversation is equal to conversation user message and then print conversation. So as you can see, the conversation class is used to manage the chat session, and we initialize the conversation object using user message, meaning this is the first input to the chatbot, and this particular line of code, print conversation, displays the conversation object before any response is generated. So here we have the user question, which are some of the best places to visit during summer. So now let's pass the conversation to the chatbot. For that, let's give conversation is equal to chatbot print conversation. So as you can see, the chatbot pipeline takes the conversation object as input. It processes the user's message and generates a response. So finally, it has printed the entire conversation history, showing both the user's input and the chatbot's response. So the chatbot assistant has told that it likes to go to the beach because it loves sunshine and waves. So now let's just try to continue this conversation. So for that, let's just give print chatbot conversation. Let's ask, what else do you recommend? So as you can see here, we created a new conversation object with a message. What else do you recommend? And you can see that the chatbot processes it as an independent input, meaning it does not remember anything that we have asked about the previous question. So since the chatbot doesn't, remember anything, it responds with some vague reply. For example, it has responded with, well, I'm not sure what else I can think of, but I do know that I'm going to miss her, which has no relation to whatever we have asked. So now our next step is to maintain the chat history. So let's do that. So for that, we need to manually add previous exchanges to the chatbot's context. So for that, we have to give conversation add message to specify role user content what else do you let me just format this. Let's print the conversation. So as you can see, this manually adds the new user message to the existing conversation object. Instead of creating a new conversation object, we appended the new message to the existing history. As you can see, this was a history, right? Here, as you can see, it came as a new question, but here it has been appended with the previous question and answer. So now let's pass the updated conversation to the chatbot, like how we did before. So conversation is equal to chatbot conversation and then print conversation. Okay, so now as you can see, it has replied with the beach is a great place to visit. There are so many different types of beaches to choose from. So now it has not given an entirely different answer. It has given us a related answer because, it was able to understand that the conversation belonged to the previous question that we have asked. So it has given us a continued reply. Basically, because the chatbot now sees both the messages, can generate a response that considers previous exchanges. And it processes the updated conversation history and provides a more relevant response. So in this chapter, we use the Hugging Face Transformers library to create a chatbot with BlenderBot 400M Distill. As you saw, the chatbot did not remember the past inputs unless manually stored. So by adding messages to the conversation object, we could maintain the context for more relevant replies. So now in the next chapter, we will see how we can use the Hugging Face Transformers to translate and summarize the contexts. In this chapter, we'll see how to use Hugging Face Transformers library to perform text translation and summarization. So it utilizes pre-trained models to translate text from one language to another and to generate concise summaries from long-form text. So let's go through the code step by step. So the first step is, of course, installing the required libraries. So the first one is pip install transformers, and the next one is pip install. So since Hugging Face Transformers library and PyTorch are not built into Python by default, we need to install them. So here we have already pre-installed it. So this step is only needed if you're running the code on your personal machine. So right now I'll just, comment it out. So here the Transformers provides access to pre-trained NLP models, and Torch enables deep learning computations, which are needed for running models efficiently. For that, we'll be using from transformers dot utils with login dot set error. So by default, transformers can generate multiple warning messages related to model loading, missing dependencies, or duplications. So this line of code disables such messages, keeping the output clean. Now next, let's start building the translation pipeline. For that, we have to import the pipeline from So from transformers, import pipeline, import pipeline and import torch. So here we have imported the pipeline function from the transformers library. The pipeline function makes it easy to load and use pre-trained models for different NLP tasks. And we have also imported torch, which helps in handling numerical computations as already told before. So now our next task is creating the translator pipeline. Let's write translator is equal to pipeline. Task is we will define the model. Here task is equal to translation specifies that we want to translate the text. And then we have given the model which loads the no language left behind NLLB 200 model, which is a multilingual translation model developed by Facebook AI. And then torch dtype is equal to torch.bfloat16. So here we use brain floating point 16-bit precision to save memory and improve performance. So talking about NLLB 200 model, so this is basically the no language left behind model, which supports over 200 languages for translation. So this specific version used here, the 200 Digital 600M, is a smaller optimized version that runs faster while maintaining high translation accuracy. So next let's give the text for translating. So let's give the text is equal to, let's just give the sun rises in the east and sets in the west. We're just giving some random sentences. Birds start chirping early in the morning. Let's give one more sentence. People wake up early and get for work. So now let's give the code for translation. So text is equal to translator text is equal to English language is equal to French. So here this src lang is equal to eng latn. This basically specifies the source language as English. Latn is because it is Latin script. And the next code is tgt, it's lang. Yeah. So this means French is the target language. So as already told, NLLB 200 model supports a wide range of languages and each is identified by a language code. So as you can see, these are the language code. ENG, LATN and FRA, LATN, these are the language codes used. So there are codes for each and every language. So now let's just view the translated text. For that, let's see the output. So as you can see, it has translated the text to French. So now next, before continuing, let's just free up some space, because since machine learning models can consume a lot of RAM, it's a good practice to free up unused memory before running some new tasks. So for that, we'll import let's write the code and then we'll explain. So here del translator basically deletes the translation pipeline object from memory, and gc.collect function runs Python's garbage collector, which clears unused memory. So it's cleared now. Next, let's start building the summarization pipeline. So first we saw the translation, now let's move on to summarization. So let's write the code. Summarizer pipeline, as you might have guessed, is summarization. So as you can see here, the task is summarization, and we have used Facebook's BART large CNN model, which is pre-trained for summarization. And then we have used vfloat 16 precision to save memory. So basically BART stands for bidirectional and autoregressive transformers, and it is a powerful model designed for text generation and summarization. So the BART large CNN version has been specifically trained on the CNN or Daily Mail news dataset, making it ideal for summarizing long news articles or reports. So let's try that out. Let's give it a text. Let's give it a pretty long text and see how it summarizes it. Sorry. So we are given a text on the impact of technology on education. So as you can see, this is a pretty long text. Now let's just summarize this. For that, let's give summary is equal to minimum length is equal to 10, maximum length is equal to 100. So here the text is a paragraph that needs to be summarized. We have given the minimum length as 10, and this ensures that the summary is at least 10 words long, and also we have given a maximum limit of 100. So now let's see the summary. So as you can see, it has actually summarized our texts. So in this chapter, you have seen how to do translation, how to convert text from one language to another using Facebook's NLLB 200 model. And also we learned how to summarize the context. We have learned how to condense long paragraphs into key highlights using Facebook's BART large CNN model. So these models are incredibly useful for automating language processing tasks, making them widely used in news summarization, multilingual communication, and AI-powered chatbots. So in the next chapter, we'll see how to generate sentence embeddings using the sentence transformers library, and we'll also see how to find similarity scores between two sentences. And also in this chapter, we'll see how to generate sentence embeddings using the sentence transformers library and compute similarity scores between pairs of sentences. So sentence embeddings allow machines to measure similarity. So let's go through the code step by step, and then I will explain it to you in detail. So the first step is, of course, installing the required library. So we have to install the sentence transformers. pip install sentence. So since sentence transformers is not a built-in Python library, we need to install it before use. However, here it is already pre-installed, so I will just, comment this out. Yeah, so these embeddings help with semantic similarity tasks, clustering, search, and more. And the next is, of course, suppressing warning messages, as we have done in the previous chapters. So we'll just paste that code. Yes. Now let's move on to the step where we will load the sentence embedding model. So let's load the model from transformers. Code sentence transformer. And let's give the model 2. So as you can see, here we have a sentence transformer. So this is a special model class from the sentence transformers library used for generating sentence embeddings. And we are using the all mini LM L6V2 model. So this is a pre-trained model we are using, which is optimized for efficient and fast sentence embedding generation. So the All Mini LLM L6 V2 version, it is a lightweight yet powerful model trained to convert sentences into numerical vectors. And it is a smaller version of Microsoft's Mini LLM model, and it is optimized for speed while retaining strong performance. So here the value L6 stands for that it means it has 6 transformer layers, and V2, as you all know, is the second version of the model with improved quality. So next, let's generate the sentence embeddings. Sentence 1 is equal to, so this is our first sentence. The cat sits outside, a man is playing guitar, the movies are awesome. It's 1, model encode. Sentence 1, convert, tensor is equal to true. So here basically what happens is we first defined a list called sentence 1, and it contains 3 different sentences, entirely different sentences, and then we converted these sentences into numerical embeddings. So that's what we have done here. We have converted the sentences into numerical embeddings using the model.encode sentence 1 function. So the parameter over here, which is convert to tensor is equal to true, ensures that the embeddings are stored as Pytorch tensors, which helps with faster mathematical operations. Basically, what are sentence embeddings? So sentence embeddings are high dimensional numerical representations of sentences. As you can see, it has actually represented these sentences, like the first sentence in this numerical form, second sentence in this numerical form, and third sentence in this numerical form. So instead of treating words individually, these embeddings capture the overall meaning of a sentence, making them useful for tasks like finding similar sentences, clustering related text, semantic search, and text classification. So now next, let's encode a second set of sentence. So for that, we'll give similar sentences. Here we have given 3 entirely different sentences again. And let's just print it. So as you can see here, we defined another list called sentence 2, which again contains 3 different types of sentences. We have encoded them into embeddings using model.encode sentence 2 function, and then we have stored them as Pytorch tensors for efficient computation. Now the next step is, let's measure the similarity between sentences. So for that, we have to write this piece of code from sentence transformers, encodable cosine scores is equal to util.cos one, comma, embeddings 2. Scores. So these are the cosine scores. These are the cosine similarities. So basically, what is cosine similarity? So cosine similarity is a metric used to measure how similar two sentences are based on the embeddings. So it calculates the cosine of the angle between the two vectors. So as you can see, these are the vectors. So it actually calculates the angle between the two vectors. So if the value is closer to 1, it means that the sentences are more similar to each other. And if the value is away from 1, or if it's closer to 0, it depicts that the sentences are not similar. So now let's just print the similarity results. So here's what this loop does. Let me explain. So it iterates over the sentences 1 list. It retrieves the corresponding sentence from sentences 2, and it prints both sentences side by side along with the similarity score. So let's see. So as you can see, the output has displayed the sentences, the pair of sentences that we want to compare, and the cosine similarity or the score of it. So as you can see, this code showcases the power of sentence embeddings and similarity scoring in NLP. So by leveraging pre-trained models like Mini-LM, we can convert sentences into numerical vectors and compare them efficiently. So this technique is widely used in chatbots where we need to match user queries with responses. It is used in search engines where it is required to find documents related to a search term. Then it can be used in plagiarism detection and also in content recommendation. Now in the next chapter, let's see how to use Hugging Face Transformers library to perform zero-shot audio classification. Hi all, welcome to the next chapter where we'll demonstrate how to use Hugging Face Transformers library to perform zero-shot audio classification, which means that the model can classify sounds without being explicitly trained on predefined categories. So this is a powerful technique that allows AI to recognize a wide range of sounds just by providing candidate labels at runtime. So let's go through the code step by step. First of all, let's start by installing the required libraries. First one is pip install transformers. Then we have install datasets. Then we have sound file. And then we have Librosa. So basically, since Hugging Face Transformers library, datasets and Librosa are not built-in Python libraries, we need to install them. So these transformers libraries used to load pre-trained models for NLP and audio processing. Then we have datasets library, which provides access to various datasets including audio datasets. Then we have the sound file library, which is used to read and write sound files. And finally, we have the Librosa library, which is a very powerful library for analyzing and processing audio signals. So here we have already pre-installed it. So let me just comment this out. So basically, to read the Librosa library, you might have to install FFmpeg. So basically, Librosa requires FFmpeg to handle various audio file formats. So if you are running this code on a personal machine, FFmpeg must be installed. So next, let's write the code for suppressing the warning messages, like we did in every other chapters. So finally, let's start loading the audio dataset. So for that, from datasets, import dataset, load from disk. Dataset is equal to load from disk, give the model. So basically, this code loads an audio dataset using the Hugging Face datasets library. So the dataset used is ECS50, which is a collection of environmental sound recordings. And each audio sample is about 5 seconds long and is labeled with different types of sounds. So instead of downloading the dataset from the internet, the load dataset, this code loads a local copy using load from disk. So now our next step would be accessing and playing an audio sample. So let's do that. So audio sample is equal to dataset 0 audio sample. Sorry. So basically, this audio sample is equal to dataset, and here we have given argument 0. That is because this retrieves the first audio sample from the dataset and prints its details. So basically, the starting is 0, 1, 2, 3. So this dataset of 0 retrieves the first audio sample, and the dataset contains audio waveforms and it is stored in numerical arrays. So as you can see, it's stored in numerical array. We have the sampling rate, we have the array, we have the audio, everything. Now let's try playing the audio. So we want to hear the real audio, right? So for that, from i-display import audio as IPython audio. We are giving the audio sample. Audio. We are giving the rate. Audio and rate. So now let's run this. So as you can see, as a result, we have got an audio file, and at this stage you should basically hear the sound being played. So I'll just play it. So yes, I hope you heard that sound. So basically this audio sample of audio and array, this is actually the waveform. This is the actual waveform data. And this particular line of code sets the correct playback speed. So once that's done, our next step is setting up the zero-shot audio classifier. So let's do that. Let's first import the pipeline from transformers. Import pipeline. Short classifier and task is equal to zero-shot audio classification, and we'll define the model. So let me just format this a bit. So basically this initializes the zero-shot audio classification pipeline. Here, as we have done before also, we have specified that we are performing the audio classification without predefined categories. And this particular model, it loads the CLAP HT-SAT model. And this is a pre-trained model designed for classifying a wide variety of sounds. So basically the CLAP model stands for Contrastive Language Audio Pre-training. So it can actually match audio samples with text descriptions without being explicitly trained on predefined classes. And the HT-SAT, which stands for Hierarchical Transformer Spectrotemporal, it is basically an architecture optimized for handling complex audio signals. So now before we move forward, let's take a look at what is sampling rate. Basically, sampling rate, or it's also called sampling frequency, it is a number of samples per second taken from an analog audio signal to convert it into a digital format. So it is measured basically in hertz, where 1 hertz is equal to 1 sample per second. So to better understand this, let's think of audio as a continuous wave as shown in the picture in the real world. So when we record or process audio, we can't store an infinite amount of data. So what we do is we take snapshots of the wave at regular intervals. So these snapshots over here are called samples. Basically, the more samples we take per second, the more accurately we capture the original sound. So for example, imagine you are taking pictures of a fast moving car. So if you take only a few pictures per second, the movement of the car looks choppy. But if you take many pictures per second, the car appears to move smoothly, right? So similarly, a higher sampling rate means better sound quality because we capture more details of the original sound wave. Now, why is sampling rate important while working with AI models? So while working with AI models for speech recognition, sound classification, and audio processing, the sampling rate plays a critical role in ensuring accuracy, efficiency, and proper audio interpretation. So here's why. First thing first, it ensures compatibility with AI models. So AI models are trained on specific sampling rates. And using the wrong sampling rate can lead to poor performance or incorrect results. So for example, OpenAI's Whisper model, which is used for speech-to-text conversion, is trained to process 16,000 Hz or 16 kilohertz audio. So if you provide an audio file recorded at 48,000 Hz, the model expects fewer samples per second, and as a result, the time duration is misinterpreted, leading to distorted or inaccurate transcriptions. And similarly, zero-shot audio classification models like CLAP are trained with specific sampling rates. So if your input audio doesn't match, the model may misinterpret frequencies or struggle to classify sounds correctly. So the thing is, always check the required sampling rate for your AI model and resample your audio if necessary. Next comes balancing audio quality and performance. So higher sampling rate means better sound quality, but also more data to process. So AI models need to balance quality and efficiency. So they typically don't use very high sampling rates. So basically, speech recognition models like Siri, Alexa, or Google Assistants, it uses 16 kilohertz because human speech is mostly within 300 to 8 kilohertz. And then we have music recognition models like Shazam or Spotify, which uses 44.1 kilohertz or higher because music contains a wider range of frequencies. So using too high of a sampling rate for AI-based speech recognition is wasteful, as it captures more detail than necessary, so increasing storage and processing time without improving results. So the ideal sampling rate depends on the use case of yours. Speech models need lower rates, while music-related AI needs higher rates. It prevents audio distortion and data loss. So when you use an incorrect sampling rate, the model misinterprets the data, causing distortion or loss of important details. So for example, if you are using a lower sampling rate than required, so if a model is trained on a 16 kilohertz audio, for example, but you provide 8 kilohertz audio, so you lose higher frequency sounds, making speech less clear. So AI models may misinterpret words, leading to incorrect speech recognition or poor audio classification, and using a higher sampling rate than required. So if a model is trained for 16 kilohertz, but you provide 48 kilohertz audio, so the extra information isn't useful because the model doesn't know how to handle it properly. So in some cases, higher sampling rates increase noise instead of improving accuracy. And next importance of using sampling rate, the correct sampling rate is to avoid temporal misalignment, which means to avoid incorrect time interpretation. So a mismatch between input and model sampling rates can cause incorrect time interpretation. This means the AI perceives the audio duration incorrectly. So for example, suppose an AI model expects 16 Hz audio, but we give it 192,000 Hz audio. So the model thinks 1 second of high resolution audio is actually 12 seconds long, causing major timing errors in transcriptions and speech analysis. So if sampling rates don't match, the model misunderstands time duration, leading to incorrect speech-to-text results or poorly synchronized subtitles. Finally, for optimizing computation efficiency. So higher sampling rates generate larger audio files, which require more processing power and memory. And AI models handling real-time speech recognition or classification need to process data fast, so they use lower sampling rates to ensure quick response time. So for example, a 1-minute audio clip at 8 kilohertz is of 384 KB, and a 1-minute audio clip at 48 kilohertz is 2.3 MB. So for large-scale AI applications, example, transcribing a 2-hour meeting, using higher sampling rates would be computationally expensive. So lower sampling rates reduce processing time, making AI systems more efficient in real-world applications. So now that you understood what are sampling rates and its importance, let's give the sampling rate for transformer models. I'll just write first and then explain it to you. Yeah, so basically this code calculates how high resolution audio, for example 192,000 Hz, appears to a model trained on 16,000 Hz audio. So 1 second of high resolution audio appears as 12 seconds to the model. So now let's see what about a 5-second audio. So 5 into 192,000 divided by 16,000. So as you can see, it's 60. So 5 seconds of high resolution audio appears as 60 seconds to the model. So this helps us understand how model processes different sampling rates. So the next step is to check the model's expected sampling rate. So for that, let's write the code. Zero shot classifier extractor, so sampling rate, audio sample is equal to audio So basically this retrieves the expected sampling rate of the zero-shot classifier model and the actual sampling rate of the dataset's audio sample. So if the rates don't match, we need to convert the audio to correct sampling rate. So as you can see, the expected sampling rate is 48,000 and the actual sampling rate of the dataset's audio is 44,100. So our next step would be adjusting the sampling rate for compatibility. So let's do that. So for that, from datasets import audio, dataset is equal to dataset cast column audio sampling rate you want to fetch the first audio sample of the dataset as we did before. Audio sample. So basically what happened is, since different audio datasets use different sampling rates, this code converted all audio samples to 48,000 Hz to ensure compatibility. So for example, we had already played this first audio sample, right? So here, as you can see the numerical value, the sampling rate was 44,100. But right now we converted the same sample to the sampling rate of 48,000. That's what we did with this code. So now let's run the zero-shot audio classification. Let's write the code for that. Let's give the candidate labels. Dog, and then we'll give a label as sound of maybe vacuum cleaner. Zero shot audio sample. Labels is equal to candidate labels. So basically this candidate labels is a list of possible sound categories we want the model to consider, like sound of dog and sound of vacuum cleaner, and then we have the zero-shot classifier which passes the audio sample and asks the model to classify it based on the provided categories. So let's see the output. So as you can see, it has interpreted the sound of dog with a probability of 0.9, which we can round it off to 1, and sound of vacuum cleaner to 0.002, which is of course close to 0. So this means that the model is 87% confident that the sound is a dog barking and 13% confident that it could be a vacuum cleaner. So let's test with more examples. Let's give more candidate labels and let's see the output of how it classifies. So here we got 4 classifications. Sound of a bird singing, we got a score of 0.6. Sound of a vacuum cleaner, we got 0.2. Sound of an airplane got 0.1, and sound of a child crying, we got 0.04. So the model basically predicts that the sound is most likely to be the bird singing. So basically this code showcases zero-shot audio classification, where an AI model processes raw audio samples, uses embeddings to understand sound characteristics and matches sounds to user-provided descriptions without predefined categories. So some of the use cases of this is for smart home devices where it is helpful in detecting alarms, dogs barking or glass breaking, and then it can be used in wildlife monitoring like identifying bird calls, animal sounds, etc. It can be used in emergency detection for detecting sirens, gunshots, or distress calls, and it can also be used in customer support automation for identifying background noise types during calls. So basically, this technique is incredibly flexible, allowing developers to classify any sound just by specifying relevant categories. How cool was that? So now in the next chapter, we'll see how to do automatic speech recognition using Hugging Face Transformers library, where audio speech will be converted into text. So in this chapter, we'll deal with demonstrating audio speech recognition or ASR using Hugging Face Transformers library, where audio speech is converted into text. So basically the process involves the first step is loading a speech dataset, then comes processing the audio samples like handling sampling rates, mono conversions, etc. Then we'll be using a pre-trained ASR model to transcribe speech. After that, we'll be building an interactive radio app where users can record or upload audio files for transcription. And then we'll be handling longer audio files and troubleshooting common audio issues. So let's go through each section in detail to understand how it works. First step, of course, is installing required libraries. So first, we will need the Transformers library. Then we would need the U datasets library. Then we need to install the sound file library. Then we need Librosa. And then we need radio. So basically these are already installed. So basically the Transformers library provides pre-trained ASR models for speech to text conversion. Then we have the datasets library which loads and processes speech datasets for training and testing. Then we have the sound file library which reads and writes audio files in various formats. We had used these in the previous chapter also. Then we have the Librosa library which is a powerful library for analyzing and processing audio signals including resampling, stereo to mono conversion, etc. And finally we have the radio library which is a library for building web-based AI applications to interact with the ASR model. So first let's start by suppressing the warning messages as we do always. Now our next step is loading the speech dataset. Let's do that. Run datasets, import, load dataset. Dataset is equal to load dataset speech ASR. We'll give this split. True 300. Training will be set as true. We'll give the trust remote code to true. So basically this load dataset of LibriSpeech ASR, this loads the LibriSpeech dataset. It is a well-known speech dataset that contains human speech samples along with text transcripts. And then we have split is equal to train.clean.100. This basically chooses the train.clean.100 subset. It's a subset which consists of 100 hours of clean speech data which is used for training. And then we have streaming is equal to true. This basically enables streaming mode so that we don't have to download the entire dataset. It is basically useful for large datasets. And finally, we have trust remote code is equal to true, which allows running dataset specific pre-processing functions. So our next step is to retrieve and view an audio sample. Let's do that. So everything is ready. Let's retrieve and view an audio sample. Example is equal to next. Idea dataset. Dataset head is equal equal to data set. We're taking the fifth one. List data set. And then we'll give list data set head 2 in the example. So basically this particular function, which is next ITR of dataset, this retrieves the first audio sample from the dataset. And then we have dataset.take of 5, which fetches the first 5 examples for quick inspection. And then here we have given, so 2 depicts the third audio sample. So now that we have got the numerical values of everything, we basically need to play the audio. So let's write the code for that. We had already written this in the previous chapter. So let's just take the code from there. So at this stage, we should hear the spoken sentence from the dataset. Let's play it out loud.
Chapter 16. I might have told you of the beginning of this liaison, whatever Marguerite wished.
So as you saw, we have played the audio sample. Next, let's initialize ASR model, build the pipeline. For that, let's import pipeline from transformers. And let's build a pipeline where the pipeline task would be, of course, automatic speech recognition. We'll give the model. Yes. So here we have given the task, and we have also loaded the Distill Whisper, which is a smaller version of OpenAI's Whisper model optimized for English speech recognition. So basically, Distill Whisper is a lighter, faster version of Whisper, and it is designed for low latency and real-time speech recognition. So it's trained to recognize and transcribe spoken English with high accuracy. So now let's check the audio sampling rate. For that, let's write this piece of code. The ASR model expects a specific sampling rate typically of 16,000 Hertz. ASR example. Example text. So as you can see here, the sampling rates matched, and here we basically sent the audio waveform to the ASR model, which transcribed the speech. Here we check whether it is true. So this printed the original transcript from the dataset. So our next step is creating a real-time transcription app with radio. So let's do that. So first let's import the required libraries and write the code. Import radio. Okay, so basically what this piece of code does is, this function transcribes speech from an uploaded or recorded audio file, and if no audio is provided, it displays a warning. Now next, let's build the interactive radio interfaces. So first is the microphone based transcription. So let's write the code for that. Using this, the users can record their voice using a microphone, and the transcribed text appears in a text box. So we have enabled the microphone based transcription. Now our next step would be to upload the file upload transcription, using which the users can upload an audio file for transcription. So we'll be writing the code for that. So basically this code allows users to upload an audio file for transcription. Now we have to combine both the interfaces. We have created the microphone based transcription interface as well as file upload transcription interface. Now we have to combine both the interfaces. So let's combine it. So this is working in progress. So as you can see, there are two tabs. One is for microphone and one is to transcribe any audio file. So if you want, you can upload the audio file over here. Right now, let's just try the transcribe microphone option. So first, let's go with a short audio recording. I'll just record one simple sentence. So global warming is a serious problem affecting our planet. Okay, let me just submit it. First, let me just hear my voice. So global warming is a serious problem affecting our planet. Okay, let me just submit it. Wow, just see this. So global warming is a serious problem affecting our planet. It has transcribed it perfectly. Now let's just try one more sentence. So let's clear this and ask another question. What is your weekend plans? Let's try this. Okay, there was some error. Just a second. Yes, and the question. Okay, it also took this audio which I spoke. And the question, what is your weekend plans? Wow, see, it also provided a question mark. See, I didn't speak about question mark or anything, but it actually read my tone and it understood. Like, it is a question and it provided a question mark. How cool was that? So before continuing, let's just close this demo. So to close the demo, we just have to write this code where it says close demo. Now, if you want to, reload it or use it again, you just have to give demo.launch and it will start the radio web app. Now that we have seen handling, shorter audio files, let's see how to handle. Let's see if it can handle, larger audio files. So let's, give a larger audio file. So for that, let's import sound file as SF, import IO. So let's just load an external speech recording for transcription. We'll see the sampling rate. Okay, its sampling rate is 44,100. So as you can see, we have a value error over here. And this is mainly because we expect a single channel audio. So as you can see, we have got a value error, and that is because we expect a single channel audio input for automatic speech recognition pipeline. So now we need to convert the audio from stereo to mono, and for that we'll be using Librosa. So let's do that. Audio.shape. We'll import SNP audio transposed dot transpose of audio in the audio transcript shape. Okay, now let's import Medusa. Here we are basically handling the stereo audio. Now let's try hearing to the audio. You converted it to mono. ASR. Yes. So as you can see, it has transcribed the audio file that we had uploaded. So till now we saw how to convert a speech to text or transcribe it. Now let's see how to convert a text to speech. So this also we'll be doing using the Hugging Face Transformers library. So the process involves is installing required libraries, setting up a text-to-speech pipeline, processing a sample text and generating speech audio, and playing the generated speech output. So let's go through the code step by step. Let's install the required libraries. Sorry, the first one is, of course, transformers. The second library is radio. The third library is Tim. Next is inflect. And then we have phonomizer. So you have to install this if you are running in your local machine. Here we already have it, so let me just comment it out. So the transformers library is to load pre-trained TTS models. The Gradio library allows us to build interactive text-to-speech applications. Then we have TIM library, which is a library with pre-trained models for vision and speech. Then we have the inflect library, which converts numbers into words. For example, 42, like 42 number, it will be converted to 42. And then we have the phonomizer library, which converts text into phonemes for better pronunciation in TTS models. Now, if you're running in local machine, you also have to install the eSpeak NG. So this is because it is a phonetic speech synthesis system. It improves pronunciation and phoneme handling for TTS models, and it is only required if you're running it in Linux machines. But if you're running the code on Windows or Mac OS, you don't need speaking. So now let's suppress the warnings. So our first step would be to set up a text-to-speech model. So for that, from transformers import pipeline data is equal to the pipeline task text-to-speech So here firstly we have initialized the TTS pipeline, and then we have given the model to load a pre-trained model for speech synthesis. So here the model we have used is Cacao Enterprise. So Cacao Enterprise has developed TTS model based on WITS, VITS, which stands for Variational Inference Text-to-Speech. And then we have the LJS speech dataset which was used to train this model, which includes female voice recordings. This produces high quality speech output with natural intonation. So this model can take text input and generate spoken audio in a human-like voice. So next, let's just give a dummy a text. So we are just given a text. So narrated text is equal to narrator text to play the audio.
Researchers at the Allen Institute for AI, Hugging Face, and time of day it was active.
So I hope you heard the audio. So this is how we converted text into speech using the Hugging Face transformers. So basically, how does TTS work internally? The first step is text preprocessing, where the input text is converted into phonemes. And the inflect and phonemizer that we used help ensure better pronunciation. And once the text is preprocessed, the next step is speech generation. So the model predicts acoustic features such as pitch, duration, and timbre, and converts phonemes into waveforms. And then finally, we have the audio post-processing. So the raw waveform is smoothed and normalized, and the final speech output is generated at the model's sampling rate. Basically showed how Hugging Face Transformers library could be used to generate human-like speech from text. So we basically first loaded a pre-trained TTS model, then we generated speech from text input, and then we also played the audio output. Now in the next chapter, we will see about object detection. In this chapter, we will be dealing with object detection. So what is object detection? At its core, object detection is a computer vision technique that enables machines to identify and locate objects in an image or video. So unlike simple image classification, which only tells you what is in an image, object detection also tells you where the object is by drawing a bounding box around it. So let's see how does object detection work. So think of object detection as a two-step process. First is recognizing what is in the image. So first, the model analyzes the image and determines what objects are present. For example, if you show it a picture of a street, it might detect cars, traffic light, pedestrian, etc. Or, if it's a room, it would detect a bookshelf, clock, sofa, stove, etc. So in this step, the model draws a box around each detected object as seen in the picture, specifying its location and size in the image. So this is known as a bounding box, which gives exact coordinates of where the object appears. So why is object detection important? So object detection is one of the most widely used AI technologies today, and here's why it matters. It is used in self-driving cars, where it detects pedestrians, traffic signs, and other vehicles to make real-time driving decisions. And then it is used in security and surveillance, where it identifies suspicious activity in the CCTV footage, example detecting a person carrying a weapon, etc. And then it is also used in retail and inventory management to track product stock in stores using cameras. It is also used nowadays in medical imaging for detecting tumors or fractures in X-rays and MRIs. And it is also used in augmented reality, where it identifies objects in real time for interactive ads. So essentially, object detection allows machines to see the world like humans, but often with even greater precision and speed. So over the years, researchers have developed powerful AI models for object detection. So let's see some of the most popular object detection model. The first one is YOLO, which stands for You Only Look Once. So this is extremely fast and widely used in real-time applications like security cameras. And then there is FASTER, RCNN, which stands for Faster Region-Based Convolutional Neural Network. So this is more accurate but slightly slower, used in medical imaging. And then there is SST, which stands for Single Shot Multi-Box Detector. So this is a balance between speed and accuracy, and it is often used in mobile applications. So each of these models has its own strengths, but they all follow the same fundamental idea: detecting objects and locating them in images or videos. So basically, how does AI learn object detection? So training an object detection model is similar to how we teach a child to recognize objects. So the first step would be to provide labeled images. The model is trained on thousands or even millions of images where objects are already labeled with bounding boxes. And the second step is to learn patterns and features. So the model learns what cars looks like, how people are shaped, and the difference between a dog and a cat. And the third step is to make predictions and improve. So after training, the model starts detecting objects in new images, and over time, it improves as it's fine-tuned with more data. So for example, if you want an AI model to detect cats, you need to show it thousands of pictures of cats in different positions, lighting conditions, and angles. So the more diverse the training data set, the more accurate the model becomes. So basically, object detection is an incredibly powerful technology that's shaping the future of AI. Whether it's helping self-driving cars navigate, improving security systems, or enhancing AR experiences, this technology allows machines to understand the world visually, just like we do. So now let's move on to see how to use Hugging Face Transformers library for object detection and how to build an interactive radio-based web app that can detect objects in an image and narrate the results using text-to-speech. Basically, the process involves installing the required libraries, loading a pre-trained object detection model, then processing an image and detecting objects. Then we'll be displaying the results with bounding box, and then we'll be building an interactive radio demo, and then enhancing the demo with audio narration. So let's go step by step. So first you'll be required to install the libraries. So as you can see, it's the same libraries that we used in the previous chapter, and I've already explained what each library does. So as it is already pre-installed here, let me just comment it out. First, let's import the necessary modules. So for that, load image from URL, render in image. Now from transformers pipeline. So basically the load image from URL, this is a helper function that loads images from a URL. And then we have the render results in image. So this is a helper function that draws bounding box on the detected objects. And then we have the pipeline, which is a function from Hugging Face that loads a pre-trained model for object detection. So now let's give some suppressing warning messages. The code to suppress the warning messages. It's done. Now let's load the object detection model. Object detection, we'll give the model. So here the pipeline object detection loads a pre-trained object detection model, and the model we have used here is Facebook DTR ResNet 50. So this is basically developed by Facebook AI, and it is based on the detection transformer DETR model. It accurately detects objects in images using deep learning. So basically DETR is an end-to-end object detection model using transformers, so it eliminates the need for anchor boxes, which older models like YOLO relied on, and predicts object locations and labels simultaneously. So next, let's load and resize the image. So for that, we'll import image. Let's give the raw image. Raw image is equal to image dot open image URL. We need to resize this dimension. Okay, so as you saw, this is our raw image. We have resized it to this dimension. Now next we have to run the object detection. So for that, let's hit the pipeline output type raw image. So next we need the same image with object detection with the bounding box and everything. So for that we need to output the processed image. So let's do that. Processed image is equal to render results in image raw image output. So basically this particular function render results in image draws bounding boxes on the detected objects, and the final image is displayed with detected objects labeled. So let's just see if it works. Processed image. Okay, I hope it's visible to you. As you can see, it has actually, drawn bounding boxes for persons, and it has actually given the score, the confidence score of the detection. So it is 99.8% sure that this particular lady is a person, and it has detected the car, it has detected the truck over here, the traffic light which is far away, it has detected these cars, these people, the handbag, as you can see, it has detected the handbag and everything. So now let's move on to creating a Gradio web app. So Gradio provides an interactive way to allow users to upload an image and see object detection results. So let's see how it works. Let's import OS, Gradio. So basically OS is used to manage environment variables and Gradio is used to create a web-based interface. Now next let's define the object detection function. So this is the code for defining the object detection function. So this particular piece of code basically takes an input image, it runs object detection using the DETR model, and it returns a processed image with bounding boxes. Now next we have to create the Gradio interface. For that we have to create a demo. Let's write the code. So as you can see, the function getPipelinePrediction calls our object detection function, and then we have the inputs is equal to gr.image function which allows users to upload image, and then we have the outputs is equal to gr.image of function which displays the image with detected objects. So now that we have worked out the interface, let's launch the Gradio app. So for that, let's write this piece of code. Demo.launch share is equal to true. Server port is equal to yes, now we have launched the demo. So basically the demo.launch share is equal to true starts the Gradio app and provides a shareable link. So this is the shareable link. Now let's upload an image over here. We have tried uploading the same image. We've uploaded the same image. Let's submit. As you can see, I'll just zoom it out. As you can see, it has detected everything as before. Let's try with one more image. We have given the image of a bicycle and a dog in a car porch. Let's submit it. So as you can see, it has detected the dog with a precision of 99.9%. Again, it has a confidence score of 99.9% for bicycle. And then it has, detected the truck. So now we need to close this demo. So for that, you just have to give this code demo.close. So it has closed the server. So now let's combine the object detection with the text-to-speech that we did earlier, so that the system describes the detected objects aloud. So I think that would be fun. Let's try doing it. So let's try the code for that. Load the output. Again, load the raw image. Let's resize it. Raw image dot resize. We'll resize to this dimension 284. Okay, so we have resized the image. So now let's write helper function to extract textual descriptions. So from helper quote summarize predictions natural language text is equal to, just copy this here, natural language pipeline output text. So as you can see, the summarized predictions natural language of pipeline output, this converts object detection results, which we saw before, into human readable sentences. So as you can see, it has given in text format. It has actually described this image in text format, that in this image there is one truck because it has detected one truck. There are 3 handbags because it detected this lady's handbag and this person's handbag. And there are 9 persons. Then there are 7 cars, and there is 1 traffic light because it has detected this particular traffic light. So as you can see, it actually described the image. Now our next step would be to convert this text to speech, which we did earlier in the previous chapter. So as you might remember, we had used the Kakao Enterprise model. Narrated text DTS pipe text. So as you can see, it is actually given as a warning that phonemizer words count mismatch on 100% of the lines. Let's just ignore it as of now. So now we just want to play the generated audio. So for that, ipython dot display import audio as ipython audio. Let's just listen to this audio.
In this image, there are 1 truck, 3 handbags, 9 persons, 7 cars, and 1 traffic light.
So as you can see, this model converted text into realistic speech, generated the realistic speech. So in this chapter, firstly, we loaded a pre-trained object detection model, then we detected and labeled objects in the image, then we displayed detected objects using bounding boxes. After that, we created a Gradio app for user-friendly detection, and finally, we enhanced the system with text-to-speech narration. So some of the real-world applications of these are in smart security systems, where it can detect people, objects, and surveillance footage, etc. As already discussed, it is used in self-driving cars, retail automation, and is also widely used nowadays in medical imaging. So now in the next chapter, we'll be talking about image segmentation. Hi all, in this chapter, we'll be dealing with image segmentation. So what is image segmentation? Image segmentation is a computer vision technique that divides an image into different regions based on what's in the image. So instead of just drawing boxes around objects like object detection, segmentation goes a step further. It outlines the exact shape of each object. So for example, you can think of it like a coloring book, as you can see in this image. In object detection, you just draw a box, right, around these cars, people. But in image segmentation, as you can see, it's colored in every pixel that belongs to a particular car, a particular person, or anything without touching the background. So why is image segmentation important? So this technique is super useful in AI applications because it helps computers understand not just where objects are, but exactly what part of the image they occupy. So it is helpful in medical imaging where it can detect tumors and MRI scans by segmenting them from healthy tissues. It is also used in self-driving cars where it can identify roads, lanes, pedestrians, and traffic signs. It is also used in photo editing where it's helpful in removing backgrounds or applying effects to specific parts of an image. And it's also used in retail and inventory for recognizing different products on shelves. So in short, segmentation lets AI see images more like humans do by identifying shapes, boundaries, and regions rather than just labeling objects. Now, what is a segmentation mask? So a segmentation mask is the output of an image segmentation model. So it's like a transparent layer placed over an image where each object is assigned a different color or label. So for example, let's see we have an image of a dog sitting on the grass with a blue sky in the background. So the segmentation will assign the green pixels to the grass, brown pixels to dog, and blue pixels to the sky, which we'll see in this demo. So basically this colored mask helps the AI understand which pixel belongs to which objects. So now let's move on to some of the types of segmentation masks. Number one, we have the binary mask. It is also called the foreground versus background. So basically a binary mask is a simple way to separate objects from the background in an image. Think of it like a stencil. So anything that belongs to the object is marked in white, 1, while everything else is black, 0. So for example, if you're detecting a human silhouette, the person appears in a white and the background stays black. So this technique is useful for tasks like background removal or object detection, making it easier for AI models to focus on what matters. And the second type is instance segmentation masks. So instance segmentation takes object detection a step further by not only identifying objects, but also distinguishing between multiple instances of the same type. So instead of treating all objects as one, each gets a unique mask. So imagine a photo with 3 cars. So rather than grouping them together, instance segmentation assigns separate masks to each car, helping AI understand individual objects in complex scenes. And the third type is semantic segmentation masks. So semantic segmentation classifies each pixel in an image into a category, grouping similar objects under one label. So instead of distinguishing individual instances, it treats all objects of the same type as one. So for example, in a street scene, all cars might be assigned a red mask while all trees get a green mask, helping AI understand the overall composition of the image. So image segmentation is like teaching AI to paint within the lines. So instead of just labeling objects, it precisely marks where they are in an image. So the segmentation mask is the end result, helping AI understand images at the pixel level. So in this chapter, we'll be seeing a demo on how to do image segmentation using segment anything model, and also we'll see how to do depth estimation using DPT, dense prediction transformer. So let's move on to the demo. So first let's install the required libraries. The first one is transformers. Second one is radio. The third one is Tim. And the fourth one is torch. Sorry, it's torch vision. So as you know, transformers is for providing pre-trained models for image segmentation. We have the radio library, which allows to create interactive web apps. Then we have Tim, which is a PyTorch library with advanced vision models. And then we have Torch Vision, which is a library which provides utilities for image processing. We already have this pre-installed, so let me just comment it out. Next, let's write the code to suppress the warning messages. Now our step is to load the SAM model for mask generation. So for that, let's start by importing the pipeline from transformers, import pipeline, SAM pipeline, SAM pipe is equal to pipeline mask generation. Let's get the model. Also here pipeline is mask generation. Here we have loaded the segmentation model, and then the model we have used here is Zygen Slim SAM Uniform 77. So it's a slimmed version of Meta AI Segment Anything model, SAM model. It generates segmentation masks for objects in an image. So SAM is a very powerful AI model that can identify and separate multiple objects in an image without predefined labels. So our next step would be to load and resize the image like before. So from the import image, I am using the same image that we used in the previous chapter so that it's easy for understanding. So let's import the image URL. So raw image is equal to image dot open, and we'll give the URL. Let's resize the raw image. We'll give the dimensions 720 and 375. So basically this is our raw image. So as of now, for faster segmentation, we'll be concentrating on a single point. So instead of segmenting the entire image, because it will take a lot of time, we can segment a specific region using a single point, and that's what we'll be doing now. So for that, let's load the SAM model in a more efficient way. So from transformers, import SAM model and SAM processor. We'll give the model names. And we will output the raw image again. So for that we want the same size, so we'll just copy paste this. Done. So basically the SAM processor, it converts images into a format the model can understand. Now the next step is to select a specific object using a 2D point. So for that we have to give the dimension. So basically in this picture I want to segment this particular person. I want to put a mask on this particular person, segmentation mask, but the thing is I don't know what is the exact dimension or the point. So let's just try with a point and see if it works. So let's just give the input points as dimension 1600, 700. I'm just giving a rough dimension. Okay. So with what this input points, what this does is this manually selects a specific point in the image. It actually selects. So for example, in this image, the particular point where the dimension comes is 1600 and 700. It selects that particular point. Now the next step is to create model input from the image at the point. So let's write the code for that. So inputs is equal to processor. We'll give in the raw image. We'll give the input points. Tensors. So basically this converts the image plus input point into a format that the model can process. And this, as you all know, we have used in the previous chapters also, this return tensors is to convert data into PyTorch tensors. So now we have to run the model for mask prediction. So let's do that. So first let's import torch. With torch dot grad outputs is equal to model input. So this basically what it does is it runs the model on the image without computing the gradients, which makes the inference faster. Now we have to convert this output into a usable segmentation mask. For that, let's post-process the predicted mask. So predicted masks is equal to processor dot image processor post process masks. This is the function. We'll give the inputs of original sizes and reshaped input sizes. So next is to find the length of the predicted masks which corresponds to the number of images that are used in the input. So we just have to give length of predicted masks. It will be 1 because we are using only one image. Now we have to inspect the size of the first predicted mask. For that, predicted mask is equal to predicted mask 0. We'll output the score. Some error. Yep, so these are the tensor values. So now let's display the mask. So for that, let's import the show mask on image from helper. So from helper, import show mask on image. Let's give the loop for I loop 3. Show mask on image. Let's see the output. So as you can see, these are the outputs. There are 3 outputs because I ran the loop 3 times, and as you can see, it has actually, given a mask on the dimensions that we have provided. I'd already mentioned that I had given a rough dimension. So if the dimension would have been more perfect, it would have, perfectly segmented this person. So next, let's see how to do depth estimation using DPT. So basically, depth estimation means it predicts how far objects are from the camera. So for that, first you have to load the depth estimator model. So let's do that first. So depth estimator is equal to pipeline task is depth estimation, and let's give the model. So here this task is equal to depth estimation loads the pre-trained depth estimation model, and the model we have used here is Intel GPT Hybrid Midas. It is basically used for 3D reconstruction, robotics, and AR applications. So now the next step would be, of course, loading and resizing the image. So first let's just load the raw image. So raw image is equal to image.open. Let's give the URL. Now we want to resize it and output the image. It's resized to the dimension of 806 is 621. Okay, so this is the raw file, the raw image. There are people crossing, so there is too much depth in this particular picture, as you can see. So now let's see how it will find or estimate the depth of this particular image. So now let's run the depth estimation model. So for that, output is equal to depth estimator. The input is our raw image. The output. So right now we have not got the output in the form of an image. We have got the output in the form of the tensor values. So basically these tensor values predicts depth values for each pixel in the image. So these are basically the depth values of each pixel in the image. So now let's process the depth output. So for that, let's write the code output. Predicted depth, the shape. So basically we are trying to resize the depth map to match the original image. So now we have to unsqueeze it. So for that, output depth So this particular code is to find the prediction. Now let's output the prediction. Prediction.shape. Raw image. So now next we need to convert the depth, this depth data. So this is basically the depth data, the predicted depth data. Now we need to convert the depth data into an image. Because finally we need the output as an image. So let's see how it works. So first we have to import NumPy. So as you can see, it has actually provided the depth image. So it is basically a black and white image, or you may say a grayscale image. So as you can see, the bright areas, I hope you remember the picture where we had people nearer to the camera, and then we had the car, the buildings, and all far away from the camera, right? So basically the brighter areas that are portrayed are close to the camera, and the darker areas are farther away from the camera. So now let's see how to build a Gradio app for depth estimation, where you can actually upload an image and find its depth. It would be fun. So let's see how it is done. So first you have to define the function for Gradio. First you have to import the required libraries. We have to import OS. We have to import Gradio. And from transformers, we have to import the pipeline. So now let's launch the app. So let's write the code for that. We have run the code. So now we have to create and run the Gradio interface. So to create the Gradio interface, we need this particular code, if is equal to gr dot interface. Just a second, yeah. So we have to launch it. The inputs we give here, the image. We have given the image type. We also define the output type. So now let's launch. We have created the interface. Now let's launch the app. So for that we will write the launch function. So I have explained you all this code earlier, because in earlier chapters also we had launched this Gradio app. Server port. Let's run it. Your app is getting ready. Let's wait for it. So as you can see in the NLP section also we had used this Gradio app. Now here we'll be uploading the image for depth calculation. We'll upload the same image so that we can compare the output. So let's upload the same image. We've uploaded the image. Now let's submit it. So as you can see, we got the same output where the nearer objects are marked bright and the farther objects are marked dark. So this basically creates an interactive web app to process the images, so users can just upload the image and they can see the depth prediction. So in this chapter we did image segmentation using SAM. We generated segmentation masks. We did depth calculation or depth estimation using DPT, and also we finally built an interactive Gradio app. So now in the next chapter we will see how to do image retrieval. So hi all, in this chapter we'll focus on image retrieval. So it is basically a technique that allows AI models to match images with relevant text descriptions. So the model used here is BLIP, which stands for Bootstrapped Language Image Pre-training, specifically the Salesforce BLIP ITM, Image Text Matching Model. So we will go step by step through the code and explain what each part does. So the steps are: it extracts the features from the image and text, it measures the similarity between the image and text, and it gives a probability score for how well the image and text matches. So first let's install the required libraries. So here we require the transformers library and the torch library, which we had already discussed in the previous chapter. I already have it pre-installed, so I'm just commenting it out. And next we have to suppress the warning messages. Yeah. Now let's load the BLIP model for image text matching. For that, let's write the code from transformers import BLIP for image text retrieval. Module name. So basically this BLIP image text retrieval loads a BLIP model for image text matching ITM. Here the model used is Salesforce BLIP ITM base COCO. So trained on COCO. It is trained on COCO. COCO stands for Common Objects in Context Dataset, and it determines how well an image and text description match. So BLIP ITM models are widely used in AI-powered search engines and recommendation systems. So now let's move on to loading the image processor. So for that, from transformers import auto processor. Let's give the model. So here the auto processor prepares both images and text before passing them to the model, and it ensures that the image and text are in a format the model understands. So now our next step is to load an image from a URL. So let's do that. So let's give the image URL. Now from till, let's import image, import requests. So here what happens is we load an image from a URL, then it uses the PIL, which stands for Python Imaging Library, to open and convert the image to RGB format, and then it displays image. So basically we want to display this in RGB format, which is normal format. So let's just see the raw image. So as you can see, we have got the raw image in RGB format. Now next we have to test if the image matches the text. So for that, let's give a text like an image of a woman and a dog on the beach. After that, we have to process the image and text. That will give inputs is equal to processor, images, raw image, text is equal to text, return tensors is equal to PT. So basically what happens here is we have given a text description. This is a text description that we want to check against the image. After that, we have given a code which processes the image and text together, and it converts the input into PyTorch sensors. Return tensors is equal to PT. So it converts input into PyTorch tensors for the model. So the processor extracts key features from both the text and image so that they can be compared. Give the inputs. So here, as you can see, we have the tensors. Now next, we have to pass these inputs to the model. So for that, let's write the code ITM scores is equal to model inputs zero. ITM scores. So this basically runs the model on the processed inputs, and it outputs the similarity scores between the image and the text. So this is the similarity score. So the higher the score, the stronger the match between the image and the text. Now let's convert these scores into probabilities. So now let's convert these scores into probabilities. For that, first let's import torch. Get ITM score is equal to torch functional softmax ITM scores into 1. So basically the model returns raw scores, which is also known as logits, which are not normalized. Now the softmax, a function over here, it converts raw scores into probabilities between 0 and 1. So higher probability is equal to better match between image and text. So softmax ensures that the scores sum up to 1, making them interpretable as probabilities. So now let's display the final probability score. Yes, so now to display the score, let's just write this piece of code. So as you can see, the image and text are matched with a probability of 0.9884, which is almost 1. So in this chapter, we loaded an image and text description. We processed both using Blip's image text matching model. Then we computed a similarity score. We converted the score to probability using softmax function. And then finally, we displayed how well the text describes the image. Now in the next chapter, we'll be seeing how to do image captioning. Also in this chapter, we'll focus on image captioning, which is a technique that enables AI models to generate descriptive text for an image. So the model used here is Blip, which stands for Bootstrap Language Image Pre-training, especially Salesforce Blip Image Captioning Model. So basically, image captioning is a process of automatically generating a textual description, as already said. So the steps involves understanding the image content, generating a meaningful sentence that describes the image, and outputting the caption natural language. So this is useful in AI applications such as AI-powered image descriptions for visually impaired users, automatic caption generation for social media platforms, and enhancing searchability in image databases. So let's just start doing it. First of all, we have to install the required library. So here you are required to just install one library, which is the transformers library. And I will just hash it out as I've already pre-installed it. Now we'll give the essential code to suppress the warning messages. Now our next step is of course loading the Blip model for image captioning. So from transformers import Blip full conditional generation. Next we'll give the Blip model. So here firstly we have loaded the Blip for conditional generation. This loads the Blip model for generating image caption. And here we have used the model Salesforce Blip image captioning base. So this is trained to generate high quality captions for images. So this model is used in AI based social media automation and accessibility tools. Now next let's load the image processor. So for that, from transformers import auto processor. Again, let's give the model over here. So here the auto processor prepares images for the model, and it ensures that the image is in the correct format before passing it to the Blip. Now let's load the image. For that, from pill import image. Now let's give the URL. So let's give the image URL. Image is equal to image dot open. Let's give the URL. Let's see the image. So as you can see, this is the image. Now let's try conditional image captioning for this. So in conditional image captioning, we provide a text prompt to guide the model. So let's just give a text prompt as text is equal to a photograph of, let's give this prompt, inputs, let's get processor, image, text, and return tensors. Let's see the inputs. So these are the pixel values. So basically this processes the image and the text together. It converts them into PyTorch tensors. So this step prepares the input so the model can understand it. That's why it's in numerical form. Now let's generate the caption. Let's give out is equal to model dot generate inputs. So this passes the processed inputs to the model and it generates a caption based on the input image and text prompt. Now let's decode the output. Let's basically print the output. So for that, let's give print processor decode out 0 skip special tokens is equal to true. So this basically decodes the model's output into readable text. That is why this code is written. And this part of code removes the unnecessary tokens. So now let's see the output. As you can see, it has actually given us the output, a photograph of a dog and a dog playing together. So this is how we tried conditional captioning. Now let's try unconditional image captioning. So now unconditional image captioning means in unconditional image captioning, the model generates a caption without any guiding text. So here we had given a guiding text as of a photograph of. So now we won't be giving the guiding text. So let's try that out. Let's write the code. Inputs is equal to processor, we need image. We are not giving text. See, here we gave it text as input, but here we are not giving text. We are just giving the image and the return tensors. Out is equal to model dot generate inputs. Now let's print and see. Let's write the code. Yes, as you can see, it says it gives the caption as 2 dogs playing in the grass. So here we haven't guided it with any starting sentence or anything. It has actually generated the caption by itself. So in this chapter, we loaded an image. We used a pre-trained AI model to generate the captions. We generated captions with and without a prompt. And we also got outputs as a meaningful description of an image. So some of the real-world applications are for AI-powered captioning, for social media automation, for accessibility, for visually impaired users, and also for e-commerce. Now in the next chapter, we'll see how visual question and answering is done. Hi all, in this chapter, we'll focus on visual question answering, VQA, which is a technique that allows AI models to answer questions about an image. So the model used here is Salesforce Blip VQA model. We'll go step by step through the code and explain what each part of it does. So basically, the visual question answering is a task where a model first analyzes an image, then processes a user's question about the image, and then generates an accurate answer based on the image. So this is basically useful for AI-powered accessibility tools like answering questions for visually impaired users. It is used for content moderation, and it is also used as AI assistance that understands images. So the first step is to install the required library. So here we need just transformers library. I've already pre-installed it. Now let's write the code to suppress the warning messages. Now our next step would be, of course, to load the Blip model for question answering. So let's do that. Transformers import Blip for question answering. Let's give the model. Blip for question answering from pre-trained, and let's give the model. So here the blip for question answering loads the blip model for answering questions about images, and this model we have used here, which is Salesforce Blip VQA base. It's trained to answer visual questions accurately, and it understands images and generates relevant responses. So this model is used in AI-powered assistance and accessibility tools. So now let's load the image processor like how we have done before in the previous chapters. So from transformers, import auto processor. So auto processor here converts images and text into a format that the model can understand. Then let's give the model to. Next, let's import the image. So from will import the image. Image equal to image.open. We'll give the image URL, which is beach.jpg. Make sure that it is in JPEG format. Okay. And now let's just view the image. Yes, so this is the image. Now we want to ask a question. So the question would be, how many people are there in the picture? So let's see what it answers. Let's give the inputs first. So the inputs would be the image, question, and the return values. Now let's print the output. Just a second. Processor.decode, we need to decode it because we need it in sentence format. And we need to skip special tokens. This is the same code that we wrote in the previous chapter. So let's see the response. Okay, sorry, we actually got an edit because we didn't define the out. So let's just paste this over here and let's just define the out first. So out is equal to the model dot generate inputs. And now let's print. So it has printed 1. We had asked a question, how many people are there in the picture, and it has printed 1. Now let's try with one more image. So now let's just give another URL of the image. So I will just give another image. Let's see the raw image first. So this is the raw image. Now I want to ask the question, how many dogs are there in the picture? So let's see if it answers correctly. So as you can see, it answered. There are 2 dogs in the picture. So basically what we did here is we loaded an image, we used a pre-trained AI model to answer questions about the image, After that, we processed the image and the text using blip, and finally we generated the output, the correct output. So now in the next chapter, which is our last chapter, we will focus on zero-shot image classification. And so in this last chapter, we will focus on zero-shot image classification, where an AI model classifies an image without being explicitly trained on predefined categories. So the model used here is OpenAI's CLIP, which stands for Contrastive Language Image Pre-training Model. So we will go step by step through the code and explain what each part does. That I'll just tell you how it works. So instead of being trained on a fixed set of labels, zero-shot learning allows a model to compare an image with a set of text descriptions, measure how well each description matches the image, and assign a probability score to each label. So this is basically useful for classifying images without retraining the model, handling flexible categories such as new product types in e-commerce, and improving AI assistance. So let's start by installing the required libraries. Here also we need to install only the transformers. We have already installed it, so I'm commenting it out. Just a second. Yes. And then let's write the code to suppress the warning messages. Okay, now the next step is of course loading the clip model. So for that, from transformers import CLIP, clip model, and then we'll give the So here basically clip model loads OpenAI's clip model for image text matching, and here the model used is clip with large patch 14. So these are trained on images and natural language to classify images based on text description. It performs zero-shot classification without needing specific training categories. So CLIP is widely used in AI-powered search, image recognition, and vision language applications. So now let's load the image processor. So from transformers, import auto processor. P should be capital. Yeah, so basically auto processor converts images and text into a format the model can understand. So now let's load the image. So from fill, import image is equal to image.open. Let's give the URL. See the image, let's view the image. As you can see, this is the image. Now let's define possible labels. Let's just give possible labels. So labels is equal to a photo of a cat, and we'll give a photo of a dog. So this defines possible categories for the image, and the model will determine which label best matches the image. So zero-shot classification works because CLIP understands general concepts from images and text. Now next, let's process the image and text. So for that, let's give inputs processor. We'll give the text, which are the labels. We'll give the images. We'll give padding. So basically this combines the text labels and the image into a single output, and it converts them into PyTorch tensors. Now we need the outputs. So outputs is equal to outputs. So basically this passes the processed inputs to the model. The model compares image with each text label and outputs similarity scores for each label. So as you can see, these are the log hits, these are the similarity scores for each label. Now let's extract the image text similarity scores. For that, let's give outputs dot log hits per image. So as you can see, it retrieves the model similarity scores for the text description. So the higher the score, the better the match. Now let's convert the scores to probability. So for that, what we need is probs is equal to outputs dot log hits per image. We'll write the softmax function like how we wrote for the previous chapter. This is equal to 1 of 0. So basically what happens is the model returns raw scores which need to be normalized. So the softmax function converts raw scores into probabilities, which is between 0 and 1. Let's do that. Let's see the probability. So as you can see, this is the probability. As you can see, we had given the picture of two dogs, right? So the first label was photo of cat, second label was photo of dog. So for the first label, we have got a score of 0.0016, which is more towards 0, which means it is lower probability as it is not a cat. And for the second label, which is a photo of a dog, it has a probability score of almost 1, 0.99. So now we want this in written form. So for that, let's just write this piece of code. And yes, we'll have it in written form where label, a photo of a cat has a probability of 0 and a photo of a dog probability of 0.9, which is 1. So in this chapter, we loaded an image, we defined possible labels for the zero-shot classification, after which we used the OpenAI's CLIP model to compare the image with labels. Then we computed the similarity scores and converted them to probabilities. And finally, we came with the output with the most probable classification. So that was it. Congratulations on completing the open source models with Hugging Face course from Simplilearn. So you have explored powerful models for NLP, translation, summarization, embeddings, and audio tasks like ASR and Text-to-Speech. For computer vision, you covered object detection, segmentation, retrieval, captioning, and multimodal VQA, along with zero-shot techniques. So with this solid foundation, you are ready to apply your skills to real-world projects. So keep exploring, contributing, and innovating.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.